to this. That's me. There is a website that has this stuff on it that you can go out to and browse around. I'm going to use a couple of pages from that website here in the presentation. A couple of notices. Everything here is the property of my company. It's protected as an unpublished work and confidential work. You may not copy, reproduce, distribute, transmit, modify, create written works, or in any other way exploit this material without written permission of me. Except where indicated, and this is in bold because it's something very important. The work I'm going to show here is not affiliated with, endorsed by, or even on the current product roadmaps of VMS software. Do not corner Camille or Daria about this. Corner me. Nothing here, absolutely nothing, should be construed as a product or support commitment by VSI software. I got up here late, so I missed the corporate directions opening. If I say anything that is contrary to what they said there, please let me know. The drivers, utilities, and programs here shown are prototypes. They are not part of the OpenVMS operating system and are not yet publicly available. Some acknowledgements. You're going to see references in here to things like Intel, Pentium, Atom, Apollo Lake, Celeron, OpenVMS, VAX, Alpha Integrity, VMS Software, Aon, UP2 Professional. These are all registered trademarks of their respective companies. We all know that OpenVMS, VMS, VAX, Alpha Integrity, and related terms are registered trademarks and copyrights of HPE. VSI Software has licensed the rights from HPE to continue to develop new versions of OpenVMS. UP squared and other references are copyright of a company called Aon Technology, and everything else I think that I leave out is owned probably by somebody else. Early on in field test, a fellow who worked for VSI called Chris Brown posted a video. And it was field test, I think it was 90G or H, running on a single board computer. Now, this is running directly on bare metal. There was no emulator, there was no hypervisor involved. And that video actually described business cases and potential uses and configurations for running x86 to process and distribute locally acquired data using low-cost commodity hardware. I saw that video and it just clicked. To me, okay, we'll get to that slide in a second, but since that time, I've continued to work with this, with x86 on single board computers. And this was actually taken from that website. This site shows software which facilitates connecting an OpenVMS Edge IoT system, and we'll describe what those are in a second, to real external world devices, interacting with that, acquiring data, controlling it, shipping it off, refining it, processing, and all that stuff. So let's start with this. What is a single board computer? Well, if you're going to talk about what a single board computer is, you have to talk about this other thing called a system on a chip. I think we all know that there are various examples of what constitutes a computer system. So let's pick one that was near and dear to my heart. This was the first VMS system I ever managed, VAX 11780. Not this one in particular, but the 780 consisted of a double-wide CPU cabinet and a single-wide I/O cabinet. That was the basic configuration. And the back of the computer had this really, really big honking wire wrap backplane that, depending on configuration, had between 40 and 50 boards that looked like this. Here's a couple of block diagrams of the 780. The one on the left is a little bit abbreviated. It shows a high-level diagram, the CPU, diagnostics, floppy drives. This thing right here called the synchronous backplane interconnect, which is where all the magic in the 780 happened. Off of the SPI, you could go out to I/O devices. There were some I/O devices that connected directly to the SPI. Two common interfaces on these were something called the Unibus and a mass bus adapter. The Unibus adapter is what went to that right side I/O cabinet. Mass bus adapters connected to things like really big washing machine sized disks, and also noisy vacuum column tapes that if you weren't careful, could suck in your tie if you were wearing. On the right is a more detailed block diagram. The data pads to make the CPU work. You had some remote diagnostics in here, writable control store. You went from the Unibus interface out to the Unibus. You went out to Unibus controllers, where you could connect things like this guy, which is an RL211, 2-disk, 2 megabyte disk controller. No, actually, you go up to 4. You could also connect serial devices to this. This is a 1-port DL11. I didn't have time to pull the DC11 out of my PDP11 right here. This is a 4-port third-party serial line card. That's also how you did your networking, using things called the DEU and A. This is a memory board and a memory controller from a PDP 1124. So you could have, I think, 3 BA11 boxes in the Unibus cabinet, and the BA11 can have 2 20-slot and 1 4-slot backplanes. I did have one of those, but I couldn't find it. So you could have like 60 Unibus peripherals connected to this. One of the really neat gizmos that you could put into a 780 was called actually any PDP or Unibus system was something called an LPA11K, Laboratory Peripherals Accelerator System. That board had a sub-processor on it. It had digital to analog and analog to digital converters on it, so you could talk to the outside world. It had watchdog timers on it. You could also put things like a DR11W, which was a direct memory access 16-bit parallel interface. And if you wanted to do it programmed IO-wise, you could put things like a DR11K out there. And that's pretty much what that 780 that I managed way back when was for. Now, brace yourself. It was a 3.5 megabyte system with a system disk that was 80 megabytes. And all the users fit on a single 500 megabyte drive. And it supported a department of about 20 to 30 engineers, graphics designers, modelers. And that system, plus a gaggle of PDP-11s, was destined to be the graphics for a Navy flight simulator. And it came with nice documentation, about 1,500 pages. The other thing that was nice about these old DEC systems was they also came with a stack of field prints. They came with maintenance manuals. When the field tech showed up, he usually showed up with a kit that had the boards for the option that you thought was broken. Fast forward to today. The YouTube video, which is out there on YouTube, but it is private, so if you want to look at it, you do have to pester BSI. Showed OpenVMS x86 running on an Intel Atom. And we'll get into why that isn't 100% correct in a second. But it was actually running on a single board computer using an Intel chip in the E3900 family of chips. This guy, $75 from Mauser Electronics. If you look at the block diagram for this chip, Remember, block diagram for the chip. You have a center I/O bus here, analogous to the SPI connector that was in 780. And you got all of this stuff built into that single piece of silicon. So you have a display, you have a memory controller, you have data capture devices, you have an imaging device, you have an audio device. You've actually got 2 USB controllers, up to 4 PCIe interfaces. 6 of they can be either dedicated 2-lane or you can multiplex them. You've got the CPU, 4 cores. You've got a graphics controller. You've got a disk controller that can have up to 2 data ports on it. You have an SD card. You have an eMMC card. You have these really neat ports called LPSS and LPC connectors. I'll tell you what those are in a second. ISH is another type of device that can go out and talk to real-world devices. You have the SM bus, which is a system messaging bus. And there's a slight difference between the SM bus and the PMC. And there's another interface out here that the CPU uses to talk to all of its internal components called a primary to sideband bus, P2SB, which Intel goes to great lengths to hide from you. This is a small piece of the 32-page table that describes the pinout for this chip. So here are the pins for the memory controller that is in that chip. Here you have the pinouts for USB connectors, a few of the PCIe connectors. Here's the SATA controller. Here are the SATA data ports. Over here, you have analog input and output devices, a fun little gizmo called the PWM, and I'll show you what that is, and up to 4 PCIe compatible UARTs. Again, we're not talking about the finished product that you see on the website. We're talking about this piece of silicon. From a device standpoint, and in some of the other driver talks you've seen, BMS can go out there and identify what's in the chip using the PCIe device IDs. There are 42 individually addressable PCIe devices inside that chip. This is the guy, the P2SB, that it took 2 years, a trip to Texas, and a confidential NDA with Intel for me to figure out how to get to it. You do have documentation for the E3900 processor family. And Intel calls these things data sheets. The first one is 224 pages. Volume 2 is 4,634 pages. Volume 3 is 6,496 pages, for a total of 11,354 pages of CPU, registers, interrupts, what you can do, bits to set, etc. If you were to print this out, this would be more paper than you would get in a ream of copying paper, double-sided. So a system on a chip is literally a system on a chip. That chip on the right, the E3900, replaces everything you see on the left, with the exception of the memory ports. When you load the Unibus cabinet up with things like serial controllers, disk controllers, analog input and output devices, it's all here. Now, a vendor will take a system on a chip and use it as the core of a single board computer. Now, both of these are very literal. What the vendor does is they add memory, they add BIOS, they add peripherals, connectors, power, etc. And this is the block diagram of the Aon UP2 Professional single board computer, which is it is around, it was around here somewhere. I had one that I actually took the heat sink off so you can see where the CPU chip is. But here's the sound. The Intel system on a chip is underneath this big honking heat sink. It's got a SATA data connector on it. It has a 40-pin hat connector. We'll get to what that is. It's got Ethernet ports and stuff on it. Really bummed that I didn't bring the little board with me. So what can you get on the Aon single board computer? Well, this is what you have. You have USB 2.0 and 3.0 chips. You've got expansion capabilities. M.2 are called small function form factor PCIe devices. You have a SATA 3 controller. You can go up to, I think, 8 gigabytes of memory, dual channel, a HDMI connector, 2 Intel Ethernet controllers, and we won't talk about the incomplete operating support list that's there. Now, what's interesting is if you put the block diagram of the Intel system on a chip next to the block diagram for the single board computer, you can see that basically the single board computer is this line down the middle of the block diagram. And what vendors do is they pick and choose what options they want to bring out of that chip and make available on their board. So if you look at it here, you'll see here are the 2 LPC low pin count interfaces that were on the Intel over there. Aon connects one of them to a trusted platform module chip. They connect another one to this gizmo called the Super I/O chip. And out of that, you have 2 UARTs coming out. This is the audio controller, which is by Realtek. They take one of the PWM modules, which is a voltage control device they use to drive the system's fan. Here are the USB ports. They take 2 of the PCI ports and connect it to an Intel chip. Which is DEUNA 10 megabit interface. This little guy down here in the corner. One Intel i210 chip. Connect one side of this to the PCI interface, connect the other side to an RJ45, and you have a 1 gigabit Ethernet connection. What you'll note, switch out of full screen mode here. There we go. Okay. So I shot myself in the foot here. We'll do it this way. All right. So what you'll notice about this is not everything that's on the system on a chip is actually brought out on the single board computer. Vendors can pick and choose what they want to implement. This little gizmo called the Super I/O chip, they use the LPC interface. The LPC interface is an alternative to the PCI interface. LPC means low pin count, lower connectivity, lower power, but that, and in the case of the Aeon boards, they're using a FinTech chip. That FinTech chip has 4 UART interfaces and a watchdog timer in it. There are lots of these guys available. So that chip up there replaces these guys. So what can you do with these single board computers? Well, you're going to see people mention things like edge systems. And that was what was in the original VSI proof of concept video. What is an edge system? It's a distributed computing component that processes data near its source rather than in a central data center. It's called an edge because it sits out there on the edge, talking and controlling physical devices that it's connected to. Why do you want to do that? Well, you do it closer to the physical data because by processing the data locally, you reduce latency, you can improve real-time processing because there isn't a distance between the data center and a water pump 3 or 4 miles away, or maybe in the next county or something like that. You're reducing bandwidth because you're not shipping stuff back and forth between this guy and the data center. And these guys, since they're processing the data locally, they can whittle it down and reduce it and send it upstream to offices or the corporate data center or people that are monitoring what's going on. Also, because it's out there next to the data, you can improve privacy and security. A couple of places where you might want to use an edge system could be a factory floor, a retail store, a point of sale system. There was a gas company in northern Pennsylvania that for the longest time had microvac systems in every one of their distribution offices. And the microvacs with a VT terminal connected to it is how they did their business that day. And at the end of the day, the 2 alphas that were in the data center would go out to all of the microvaxes and do a DECnet copy and copy in what every office did that day. Another place that you could put a system, and this is a focus on the responsiveness of the system and also the data security and privacy, is a classroom. This thing could sit on a local area network in a high school classroom and host an entire computer science class. IoT systems, they're kind of an extension of an edge system. It's basically a bunch of edge systems that are put together. IoT is the Internet of Things. They talk to each other. They can do, they give you the ability to do things like remote control, data analysis, automation. They can have sensors and software to collect data about the environment that they're sitting in, and they can also control the environment that they're sitting in. So, why was VSI looking at, and again, they were looking at it. This is not a current product, not on their roadmap. Internally, this project has gone the way of the dinosaur with VSI. But what's interesting, what's good, why might you want to put OpenVMS on an edge system? Remember, an edge system sitting way out there, outside of the data center, outside of firewalls, maybe in a box in a field connected to a seismic sensor. There are SBC computers that are manufactured specifically for the railroad that have interfaces on them that talk to things like trackside sensors, control the oilers that squirt the graphite on the tracks and the oil when a freight train goes by to lubricate the wheels. You want those systems, number one, to be there all the time. You're not putting a very expensive system out there in the field, so there's a lower cost of hardware. We all know that OpenVMS, if you're lucky, you get maybe 1 patch kit a year or maybe 2, so it's a lower cost of maintenance. We all know security for OpenVMS, cool and unhackable. So it's going to be, in my opinion, very difficult for somebody to walk up to a VMS system into the field and break into it. Not impossible, but if your favorite Linux or Unix hacker is able to pull the top off of one of these boxes and he connects his laptop to it, he's going to see a prompt that says username. Scalability, and this was highlighted in the VSI video. We all know that VMS scales very well. One of the things that makes it scale is clustering. The VMS that's running on these SBCs, it's the real VMS. There's nothing taken out of it, including the ability to cluster, including the ability to run DECnet, including the ability to run IP. It's the VMS that we know and love. So one thing that you might want to do is connect a couple of these guys together, maybe in the bottom of a commercial kiosk or something, and it's controlling the screens that somebody uses when they go by, an information kiosk, maybe an ATM. Yes. So if you think that you might want to put VMS on a single board computer, what are some of the things you got to look at? Well, just like any other computer installation, you have to look at your power requirements, connectivity, storage, network connectivity, what redundancy and stuff that you want to use. But you also have to say, since this is at this point, a Midnight Skunkworks project, I mean, does VMS boot? VMS has always, forever wanted a serial console. Not quite, it got a little bit easier when they did the guest console for 9.2-3, but VMS always know how to use and always wanted and always did good things with the serial console. You have to be able to recognize storage devices and you have to be able to recognize network devices. Not that you can't add more stuff to it, but right out of the box, you want to be able to get VMS up and running on this. And the video was done, the VSI video was done during early field test. It was before the Intel driver had even got the smarts in it for the Intel chips. So you could log in, you could do a show CPU. It said you were on an Aon UP2 Professional. And let's see there. Yeah. This is the original OpenVMS Edge system. It was the Aon UP2, not UP2 Professional, UP2 board. If you look in the BIOS settings, it had the ability to take the commands that were going out to an HDMI monitor and send them out to a serial port. It had a PCIe-based UART ports, one of those 4 ports that were inside the Intel chip. They actually brought out to a debug header on the board. So on that board, you would get TTL level transmit receive data. You run that through a little gizmo like this that steps them up to RS-232. You can connect the DB9 connector to it. And you're actually talking to VMS's OPA0. Another option for this is they have these boards, these little adapters that instead of ending in the DB9 connector, they actually end in a USB connector, and it's got a USB to serial adapter on the chip. So you connect your laptop to that guy, fire up your favorite terminal emulator, and as long as it has whatever drivers it needs for what's on the end of the USB, like FTDI, for example, you hit return and you're looking at a username prompt. So we had, it recognized a storage adapter. It had a single SATA port. It did have the EMCC port, and you could reconfigure that to be a second SATA device. Had USB connectivity. It had a 40-pin connector that was compatible with a Raspberry Pi. So all those little neat gizmos that you can go and buy from a company like Arduino could plug into this board. But the network connectors, the network chips over here, were Realtek. OpenVMS doesn't have a Realtek device driver. At the time that this was being done, The UP2 was on its way out and it was going to be replaced. Oh, here it is. The UP2 Professional that had has the heatsink off. There's the system on a chip in the middle of it. This was the replacement to the UP2. This is the UP2 Professional. And at the time, I was corresponding with the people in VSI that were sort of involved with this Skunkworks project. Because I had talked to the Aon folks, I got a pre-release of what the specs were for the UP2. And when you looked at that, it looks very similar to the UP2 Professional. It has a PCIe-based UART console redirection, the same type of SATA port. But look here, Intel i210. BMS knows how to talk to an Intel driver. There were some engineers and myself, one of which is in this group, that we did some late night correspondence on. And within a very short period of time, we had, there was a driver that allegedly would run this chip. PWM, GPIO, the I2C interface is really neat because there's a lot of stuff you can connect to an I2C. It's PCI expandable. They took the two of the PCIe interfaces, brought them out to the Intel chip, and connected to the RS-232, to the RJ45 connectors. They took another 3 of the PCI connectors and brought them out to the M.2 low form factor. There's another name for this. So you can plug PCI cards into it. They reused a lot of the stuff that came from the UP2, so it's the same SATA controller. With the PCI expansion ports, it gives you the options of putting in things like this, which is a 4-port UART. So what I'm holding in my hand replaces half of a DZ11. This guy is a complete implementation of an Intel i210 board. So plug this into one of the expandability slots, and you have an extra Ethernet interface for BMS. So that means you could actually set one of these guys up like I like. It's IP on one interface, DECnet on another interface, and the cluster protocol on the third interface. But one thing that they didn't do, they did not allow you to take the eMMC port and do it as a SATA device. So you're only going to have DKA0 on this system. And further on down the road, when you actually get VMS out there and take a look at it, this is what VMS is seeing. Now, there are some drivers that were added to this. This is the native kit SATA driver. Here is the network port, EIA0, EIB0. Someplace we've got SR driver, which is the console serial port. And basically, this is how the exec goes out there and figures out what it's running on and what devices it can see. You can do these same commands with VMS under a hypervisor. You'll notice in here that there is not something called the P2SB. It took me a long time to figure that out. And there are also some extra devices out here. You'll see an XW device, an XP device. You'll see additional terminal ports down here. And that's what the UP2 Professional looks like. As I said, this 40-pin hat connector here is Raspberry Pi compatible. So this is a Raspberry Pi breakout box that brings all of the connectors that you can connect those neat little devices to the outside world, connects them to LEDs. These are the 4 lines that come off of that 4-port PCIe card. This is the second PCI UART interface that comes off of the 40-pin hat connector. This is the console port, again, through one of those little TTL to RS-232 converters. That's your OPA 0 connection. And the diagram there on the lower right from the vendor, actually the chip vendor, says this is how you can take single board computers and connect them to the outside world. Connect them to a card reader, maybe a barcode reader, a thermal printer. I saw another diagram that showed one of these guys in the bottom of an ATM, talking to the ATM over a serial port. And that diagram actually came from the ASICS website. ASICS is the maker of the AX99-100 chip, which is a 4-port serial card, M.2 slot. That's what it was. So, and this is what things look like from a VMS system. This is 5 users logged into TTA0 through TTE0. And just for the heck of it, as the system manager, I hit the console port. So right down there, you do a show process /full/node, and you see we've got 6 processes on the system logged in. So what can you do with this board? Well, one of the things you can do is you can actually control the outside world. This is this shows 16 GPIO ports for output only. They're connected to the Raspberry Pi hat connector. And what we're going to do is we're going to run a program which basically increments the logic levels on those 16 output lines. So this is actually live. There's the program I'm going to use. I run it. It gets chatty on the terminal when it runs. I don't know why it flipped it, but if you watch the lights here, as each one of those GPIO signals goes high, you see the light on the breakout board correspondingly go high. It'll walk all the way across, and then it'll walk them down, so it'll go out. I actually have a program that sort of emulates the rotating light pattern that they had in the front panel of the 1170. But you can put things like relay control boards. Oh, no, not quite. Is that here? No. Let's stick to the script, Jim. So that was the GPIO lines. The other thing that was on this chip was this thing called the PWM. A PWM is a pulse width modulation interface. It gives you the ability to approximate an analog output signal with digital signals. There are little boards that you can get, like this board right here, which is a motor control board, which takes PWM signals and using GPIO signals, it can turn power on and off. It can control the direction. And what we're going to do here is we're going to run a little program that, very similar to the GPIO program, adjusts the PWM level up and then adjusts it down. There is a light connected to the motor control board. The motor control board is also connected to a multimeter. So when this guy actually runs, you're going to see the light intensity. At first it starts all the way up and then it ratchets down. And if you look at the multimeter here, again, I don't know why PowerPoint decided to turn this thing sideways. You can actually see that the voltage on the meter is changing. This is live. Well, recorded live anyway. And when you put all of those things together, With the GPIO signals, you can control direction. With the PWM, you can control intensity. So here's a program that connects GPIO lines to the motor control board and the PWM. So not only can I control the intensity of the voltage going out to what could be a motor that's running, I can also control the direction. You've got two lights over here that are connected both to the same output source, but these go through opposing diodes. Since this is direct current, they will only light when the current goes in the direction that the diode wants. So as soon as this guy fires up, which should be like right now, you're going to see that the lights are on. They change intensity as we go up and down with the PWM voltage out there. I'm using one of the GPIO signals to control current direction here. So that's why these guys are switching. When I do that, since I'm switching the direction of the current, the lights alternate. And if you look really carefully over here on the breakout board, you'll see the output of the 40-pin connector from this board doing its thing, going out to the voltage control meter. Well, gee, that's nice, running lights and light bulbs and stuff like that. But what can you really do with this? You can really do and he lied to me. Come on. And nuts. You're going to do this, aren't you? He told me I'd be able to display both. Oh, there we go. This page is actually designed for a larger, darn it. Yeah, this is live. It's designed for a larger monitor. Shoot. I hate Windows. Nuts. Well, I'm afraid I'm going to actually have to send you to the website to look at this, which means you won't be able to see the model trains running at the end of the presentation. But the example I'm actually trying to bring up, which looks really nice here, is the display setting. Well, during the break, which I wasn't expecting to take, maybe I can go out and find the guy and figure out why this thing isn't working. Nuts. Anyway, the demo I was trying to show you, which you can come up here and look at, actually shows a segment of a model railroad. And the train runs around the loop, and then VMS figures out where it is, backs it up, puts it onto a siding, and stops it. Anyway. Okay. So that was the GPIO. So I went looking for other single board computers that would be good candidates to run VMS. And one of the guys that I found was this guy from DFI Systems. It uses the same Intel processor, the E395040 or 30. It's available in various memory configurations. It has the same type of disk interface on it because that interface is built into the chip that they're using. It does use the, don't see it here, but the chips that are being used are the Intel i210 chips. It's got 4 DB9 connectors on it. The last DB9 connector can be configured either as a serial port, right here, or a 9-pin GPIO port. So you can have 9 analog outputs and inputs. This guy boots and runs VMS. You hook your distribution kit up to it, and you'll eventually get to the menu. It does have inside both a SATA connection as well as a slot for an eMMC card. You can take that eMMC card and you can configure it and connect it to the SATA controller. So this will be a 2-disk DKA0, DKA100 system. As you're installing VMS on this guy, it sees the 2 network ports. You can configure IP and DECnet. The link lights come on. The console knows if you plug the Ethernet cable in and out, but for some reason, interrupt traffic is not getting from the controller to the device driver. I have gotten a couple of ideas of what to look at. There's the outside chance it might be fixed in an update kit, which brings up an interesting story. Remind me to tell you how you get software onto a system that you absolutely can't talk to. It's a really interesting story. And I actually have everything up in my room right now that I'm going to go probably tonight and see what this thing does with 9.2-3 and update 2. The console port on here is a little twitchy. It eventually loses it after a while. Things get better with the 9.2-3 guest console because there I'm going out the HDMI port and not the serial port. What happens with these Super I/O chips is built into them are all of these devices, but there's a setup you have to go through. Sometimes it's selecting which option you want. Sometimes it's moving a map window around so that the I/O memory into that chip overlaps the registers you want. The UART driver for VMS is really, really simple. It's the 8 serial connections that PCs have been dealing with since the dawn of time. It doesn't know how to talk to the Super I/O chip and say, I want you to give me access to your UART. And once I have access to the UART, then I'm going to pump data in and out of it. So this guy I have high hopes for with an OpenVMS update and using the guest console. Okay, you know, we've been talking about this thing called Atom and Apollo Lake and stuff like that. And the original VSI video describes something called Intel on the Atom. Well, that's kind of not right. Intel Atom is a family of low power, low cost x86 and x86-64 system on a chip. The Intel 3930, 3940, and 3950 belong to a family of processors that are called Apollo Lake. So the proper way to refer to this is OpenVMS x86 running on an Apollo Lake system on a chip. Just like those nice diagrams that we used to get from the HP folks that showed how the various integrity models, Montecito, et cetera, progressed up. There are follow-ons to Apollo Lake. There was something called Gemini Lake, and then that went through a Gemini Lake refresh. There's Elkhart Lake, there's Alder Lake. Seed, the company that makes a lot of these little devices that you can connect to that 40-pin Raspberry Pi connector, had a Gemini Lake-based system that they called Odyssey. It actually had, in addition to the Arduino and Raspberry Pi compatible connector, it had a board resident coprocessor on it that also had ways for it to talk to the outside world. The coprocessor and Apollo Lake actually shared common memory. So VMS could load a program into the coprocessor and kick it off and get it to run. They could communicate back and forth. Unfortunately, well, first off, even when you could order this board, it was almost impossible to get. That's how popular it was. It is now absolutely impossible to get. I don't even think they're available on eBay anymore. I really would have liked to have tried x86 on a Gemini Lake Odyssey. But there are lots of other vendors that are taking these boards and they're using Elkhart Lake and Alder Lake as their central SoCs. So what do you need to look for if you want to try VMS x86 on a different single board computer? This board is a follow-on to the UP2 Professional from Aeon. It's the Upsquared Pro 6000. This was actually looked at by, I think, a customer of VSI. And it looks kind of sort of similar to the UP2 Professional. One thing that hardware designers like to do is if they have a design that works, they like to reuse it. Now, remember, all of this stuff is also going into the silicon. So the chip designers, the guys that are designing the dies and everything, it's really easy for them to take a design that works and just transfer into it into another SoC. This guy had both. This guy had both I210 and 2.5 gigabit networking. But this guy down here, they used a different Super I/O chip down here. When you go and look at what it takes to get into that Super I/O chip and get to the devices, it's really, really complicated. Again, the guest console might make this a little bit easier, but about at the same time that I was giving up on looking at the 6000 series, I think the VSI customer gave up on it as well. But while I was looking around at the 6000, I came across the 7000. I have a really, really strong feeling the same hardware design team that did the UP Professional did this board. Because if you look at it, it's got the same family Super I/O chip, the FinTech down here. It's got the same 40-pin hat connector. It's got the USB connectors. What they did do in this board is they took the eMMC port and allowed it to be attached to the SATA controller. So you would have a DKA0 and a DKA100 on this board. It does have the Intel 2.5 gigabyte networking, but it has the M.2 PCI expansion cards that you can put one of these guys into. So in theory, OpenVMS should be able to make some sense out of this board. I have not gone through and done a detailed comparison of the registers for the SATA controller on this chip to the UP2 Professional. Since this is on a different chip, the high order hex identifier of the PCI device identifier is going to be different. For those of you who were around last year for Gary's boot manager presentation, Gary explained how those PCI device IDs work. There's a big database of it. He actually regularly goes out there, snags those, pulls it into the boot manager. So the leading value tells you that it's an Intel option. I think it's 8086 almost exclusively. And the bottom half of the PCI device identifier will say it's an Ethernet device on this particular system on a chip. Along with that 2 years of work, trip to Texas, and executing the non-disclosure agreement with Intel, I now have access to some of the NDA manuals that describe these chips. And as I said, I haven't gone through the legwork yet of comparing the older Lake SATA controller to the Apollo Lake SATA controller. I'm hoping that they're both similar. But you knew that there had to be a but. Oh, before we get to the but, this is another guy that I came across. Best way to describe this single board computer is it's a monster. It has two 2.5 gig network connections here, but on the bottom of it, there is an expansion slot that you can put an adapter in and actually break the multi-lane PCI controllers out to single PCI expansion slots. So here you could put two Intel boards that on a good day VMS will recognize, and you would have an EIA0 and an EIB0. It has 4 SATA data connectors on it. So this is a really good candidate for a system installed the way I like, which is everything that makes the VMS system just run on one device and everything else on the other. You put the SATA cards in here, and shadowing will keep the two of them together. So you have a redundant system disk and a redundant data disk. At some point, if a driver for these ports becomes available, you can use LL driver to run primarily on the 2.5 gig port, but fail to the 1 gig port if there's a problem. So that guy looks very promising. And now we get to the accept. On both Alder Lake SBCs, 923 doesn't make it through sysboot. Don't know why. Probably an instruction set thing. But the other thing is that as these SBCs get more complicated, the number of knobs in the BIOS that you can twiddle grows exponentially. The CPU setup page for Apollo Lake is maybe about 3 options. For Alder Lake, it goes on by pages. And there are just too many combinations that start going in there randomly, figuring out what CPU option is or is not there that is giving sysboot serious gastric distress. Okay, now we get to the personal opinion portion of my presentation. You're about to take a dive into the OpenVMS world according to Jim. In case you haven't figured it out, I'm Jim. Technical challenges for supporting OpenVMS on a single board computer. One nice thing about having these standard devices is that everybody can put them together their own way. So just because you have a single board computer that uses the same components, those those single board computers can behave differently. One example, that 40-pin hat connector that you see on the UP2 Professional, it has 5 and 3.3 volts coming out to the voltage spots that you would have on a Raspberry Pi. Those voltage leads are under power all the time, as long as the device is plugged in. Whether or not it's on or not, those voltage pins are hot all the time. So if you want to pick power off of those guys to drive, say, your RS-232 converter, that RS-232 converter is going to be under power for as long as that guy is plugged in. That could be a problem if you wanted to use that guy to drive a chain of external, say, I2C devices, because you're not going to be able to turn power off on those in a safe way. Not all of these devices, actually all of these devices, I'll make a generalization, do not react very well to power spikes. That's why the heatsink isn't on that board anymore. I did blow that board up. Note to self, when I get around to it, we're going to use these little things called opto-isolators to isolate the output devices from the CPU board. Generally speaking, the more complicated the SBC is, the more options there are in the BIOS setup. BIOS setup can affect how different components behave, what features are available. And they may even change the behavior of additional options as you plug them in. So how do you support diversity like this? The technical solution in the OpenVMS world, according to Jim, is you do it on very specific, vetted and tested single board computers that are using specific systems on a chip with options that you know work. In some cases, these might even be things like you have to use this specific part that you order from this specific vendor. Very similar to what BSI is doing now with fiber channel pass-through, 3Q logic cards with very specific part numbers. You are going to have very specific BIOS settings and options. And if you say, you know, I want to see what this option does, you're on your own. Okay, a business challenge for running OpenVMS on single board computers. This is a real customer quote, several years old and sanitized, so I don't give away who this was for. This is an Integrity RX 2800 i2 server with an OpenVMS HOE license. It was being added to an existing cluster. The total cost after the HP partner ran all their magic discounts and everything was $64,609. You break that down, approximately 40% of that was software licensing and support. So the hardware cost roughly $38,000 and the software cost roughly $25,000. I think you're starting to see the problem here. How do you do this when the whole cost of the hardware could be under $400 or $300? Another way of looking at it is consider OpenVMS as a retail product with VSI as the producer wholesale. And the unit that you're producing is a single user OpenVMS license with support. There is a minimum cost to producing that object, that widget. That cost includes development, testing, and quality assurance, not quality insurance. Although maybe in the case of VMS, it is insurance. The cost of raw materials, the hardware that is developed on, the facilities costs of that hardware, keeping the lights on, administration. I don't know what this number is. I'd really like to know this, but I don't. But I think it's a safe bet that this is going to be more expensive than the cost of the single board computer. So how do you address this? In the OpenVMS world, according to Jim, you don't. This is not VSI's fault. There is a reason that the person with the single board computer wants to run OpenVMS on that hardware. See the previous slide, why OpenVMS is good for edge systems. I used to say that OpenVMS contains man-decades of quality engineering. I have now revised that to be more accurate and politically correct. The OpenVMS product has person-centuries of quality engineering, design, QA testing, development and testing. There is a cost to that. And if you don't like it, go run Linux. This is not VSI's fault. So again, in the OpenVMS world, according to Jim, there would be a line item part number for a single user OpenVMS license on an SBC, and it would probably be more expensive than the commodity hardware. Don't like it? Don't run VMS. But the way I think you make this work is bundling. And no, I'm not a car insurance salesman here. But if OpenVMS on a single board computer is going to be used and integrated into a customer product, then that manufacturer will probably be buy a lot of them. And they're also going to need development systems. And those target configurations should largely be the same. So theoretically, there is an economy of scale of supporting 100 of these boards where they're all the same. So that could make the bundling and the licensing costs a little bit more palatable. One way to do this might be to offer licensing add-ons to a virtual environment or to an OpenVMS physical server that these guys would be connected to. Maybe you offer licenses that have licenses for 10, 20, 100, maybe 1,000 single board computers. Now you're actually starting to get into the economy of scale that we saw with traditional servers. But I don't see any way that a single user license for a single board computer is going to be in line with the cost of that hardware. Now, with that said, there are versions of that hardware that are ruggedized, or versions of that hardware that are militarized. They cost more. So there you're potentially closing the gap between the hardware cost and the licensing cost. Also, if you're talking military, you're talking US government, and when's the last time you knew that the government cared about how much things cost? So how could you do this? One possible solution. Take a look at a sample bundled installation. Consider a manufacturing line, which is controlled by OpenVMS single board computers. Up and down the manufacturing line, you have multiple devices for multiple sampling points, multiple control points. They're also there for redundancy. These guys would do something that OpenVMS x86 can't do right now, and that's a satellite boot to a main server. The main server could be a virtual or a physical server on the bottom with shared storage between them. In this configuration, we've got all the stuff available to us that we've come to know and love with VMS. Failover, rolling updates, rolling reboots to put in patches. One guy goes down, the other guy takes over. If this is starting to look like a disaster-tolerant cluster, it is only because it is. But gee, what about, oh man, I gotta go out there and I gotta add a quorum node, a high-priced server that's gonna sit there and not do anything. There's your cluster configuration. And your quorum node is another single board computer sitting on the side. This is a 3-node voting x86 theoretical OpenVMS disaster tolerant cluster. This could be for a manufacturing line. This could be for a gaggle of ATMs in a kiosk in a bank lobby. This could be for customer information displays in an airport, you know, the ones that actually went belly up with that little Microsoft, yeah, that's the one. CloudStrike, that's it. Yes, and I'm a proud owner of several of the t-shirts from the last Bootcamp that says CloudStrike. What's that? I run OpenVMS. Other possibilities, you can have isolated systems that do individual process control. I have a built-in swimming pool on my lower patio. I'm kind of obsessed about keeping the chlorine level at the right level. There is a floating sensor I can drop into the pool, which is wireless capable, that will do sampling of the chemicals in the swimming pool. If I can get an OpenVMS process to go out there and ask the sensor, tell me what the chlorine level is, then the application running on the VMS system is going to know what it should be, the volume of the pool, the concentration of the tank of sodium chloride that I have sitting outside, connected to a little chemical pump. Chemical pump is on a circuit relay that is activated by one of the GPIO lines. VMS figures out how long the pump has to run to bring the chlorine level to where I want it. It turns it on and sends me a VMS email saying, you might want to go take a look at the pool. Now, how can we help this effort along? The ISV and the hobbyist community can help. They can be the ones that not only flush out the hardware that works, but they could also flush out potential business opportunities for this. I did talk to Daria about this last year, and very rightly so, she said, we have to do the marketing research on this, we being VSI. This group will need a coordinator. I volunteer. There was an original group of people working with the original Aon board. I'd like to get that band back together again and add some new participants. This group would work issues before they become whittled down to a single problem that we can categorically state, this is what we're seeing, and get it to a point where it's not hopefully going to take a lot of additional work on VSI's part to look at. But the thing we have, again, my opinion, my VMS world, is we have to take the burden of doing this off of VSI. So if you're interested, let me know. There's my email address. There's the website, which unfortunately I'm going to try to get back up on the board right here. Again, in the OpenVMS world, according to Jim, I would like there to be a term called an acknowledged system. An acknowledged system is a single board computer that runs OpenVMS x86, and VSI will make a best effort to keep it that way. Right now, there was one of these guys, and that's the Aon UP2 Professional. I'm hoping that there will be more. How do you add to this list? That's the ISV and the hobbyist environment description that I just went through. Bottom line, OpenVMS needs a paying customer to do this. Because OpenVMS right now is in a fundamentally different place than when OpenVMS engineering was part of HPE. Days of VMS engineering being able to do something because it's neat and cool just doesn't make business sense. Not that the people that are in VMS engineering don't still want to do the right thing, but there's a business reality behind VSI. It's a standalone company that wasn't there when HP VMS engineering had the big HP company behind it. So it has to make business sense. Unfortunately, my model railroad doesn't fit that bill. Doesn't mean I'm still not going to work on it. But there are a couple of people that I've shown this to that are interested. I showed this when I made that trip down to Texas. I brought one of those boards with me and showed it to a guy who I suppose had the same amount of gray hair as I did and remembered things like VMS and batch. And I said, this is real VMS, what you remember. He said, send me an email on this. I got a couple of guys that might be able to do some fun things with this in their lumber mills. But opportunities like that have to become real business realities.
AMD, Frederick for AMD is an engineer's project.
Ah, okay.
That's how that came a business sense and they captured the market.
Yeah. You know, I mean, I'm out there when I talk to application people all the time saying, you can now, and I give them the approach that VSI is putting out there. VSI on x86 hardware or under an x86 hypervisor, it's no longer the one-off funny stranger in the data center. Probably about 20 years ago when I was having a discussion with somebody in Citibank who was absolutely committed to Unix, I said, the trader up on the trading floor doesn't care if his quote comes from a Linux or a Unix or a VMS system. He cares when he can't get it. So that's my take on all of this. And now I'm going to see if I can finally get this thing back up on the big screen. Questions, comments? In the case of the UP2 Professional, you burn your distribution kit to a DVD, plug it in, and boot it. And the boot manager will figure out that it's booting an ISO kit. It'll load the entire distribution kit into memory. You drop to the command level, you say show device D, it'll say DKA 0. You go back into the menus, you say install, and away it goes. When it comes back up, it says you go into net$configure advanced and TCP IP $config. It says you've got an EIA 0 and an EIB 0 device. What do you want me to do with them? You can configure DKA 0 as a single member shadow set. Let's see if we can get this. Where is the freaking control panel? Settings. Go take a look at the website. It's got a lot of neat stuff out there. There's more stuff I just haven't gotten to. System display. Display. Extend. Duplicate. Ah, okay. This. Have that. Back here. There we go. This is written for a larger display. Over on the right, you see live commands. What's going to happen here is that the model railroad is actually going to make one loop around. VMS is going to keep track of where it is. When it gets to the right segment of track where it knows that it can switch to a siding, it's going to slow it down. Then it's going to reverse it and back it onto the siding. On the bottom, you see the Raspberry Pi breakout board connected to motor control relay and also to a PWM-based voltage control. He's going to come around. He's making his first loop. Over on the right, you're going to say, okay, I should start a parking operation now. Where are you? He's coming around. He's slowing down. This is all done reading RFID tags, which are on the bottom of the train. Okay, the end of the train just came to where it needed to. Flip the switch, back it up. And we're done. And that edge system right there in the lower left corner is sitting on a table that's slightly outside the frame. So it is at the edge of the model railroad. Yes. I am going through TT drive. The there it is, show CPU. It's the Aeon UP2 board. TT driver is, as you know and love from VSI engineering. I took the UART serial driver and basically made it understand the PCI-based UART. Once I had it properly mapped, the UART devices, the UART devices line up with the bit definitions that OpenVMS wants. The port driver does its thing and talks to the class driver. And now you've got TTA0 through TT E0. The RFID reader is this guy right here, the track, connected to a serial port, which goes there. So my little multi-thread P-threads based program starts one thread for every RFID reader, and they coordinate their access using P-threads, and there's a common database and all that fun stuff. I wrote that too. Now, let's see here. Other thing we can do. Actually, here's how the RFID reader works as soon as it loads the rest of the images here. Basically, I'm using an RFID reader, which is a PN532. It's connected to VMS device TTB0. Load the rest of it. You're going to make me do it this way, aren't you? Get out of the way. Yeah, disclaimer, this was looking for a much larger display. Serial RFID. Oh, no, not that. So actually, I don't know if you just saw it, but I'm logged in on TTB0. Yeah, there's TTE0, which has the RFID reader connected to it. There are the settings that are part of system startup to set the terminal settings. And now I'm actually going to run the reader control program. It says I'm ready to do a tag read. It spits out the registers and stuff that it gets back from the RFID reader. Yep, yes. So which means I have the TT driver type ahead buffer available to me. Yes. And should pick up one of these tags in a minute and actually pass it over. Where are you? Oh, it's this laptop. Look, this is actually coming from the website. But there is another, where is it? Control GB, control relay. Yeah, this low power laptop is having a problem. But the next thing is if you actually pick up one of these RFID tags and pass it over to the reader, it'll tell you what the tag value is that are read over there. So let's kill this right now. And if you go to the main demo, which is down here, this is the full-blown edge application. Controlling the actual model railroad on the bottom. I'm talking to RabbitMQ, which is running on a Linux system there. We're going to use RabbitMQ to fire off some commands, which are going to be dispatched to the control process. And as it goes around the layout, you're going to see the switches activate. You're going to see position updates over here. And I need to get further over to the right. There you go. Okay, that was me starting things up. There's a publishing thread that starts to send information out to RabbitMQ. I think the windows might be a little bit out of sync here. But eventually you're going to see that I'm going to go back to the RabbitMQ GUI and actually pump command out. This is actually running on this board, the Odroid board. This is actually dual boot. It runs Linux that has KVM on it, so I can run the RabbitMQ server on it. It also has a KVM interface, and what I'm working on getting done is having a virtual VMS instance that talks to the SATA disks using a pass-through. So the DKA devices in the virtual machine are going to be the same DKA devices that are on the physical box when I get through, hopefully, the Older Lake boot problem. Why might you want to do that? Well, think about what if you want to write a device driver for the disk controller that's on the SCUF? How do you do it when there's only one controller to get the VMS? Well, the answer, I think, is you take the PCI pass-through for the SATA controller, pass it through to the virtual machine. You log into the virtual machine and you do your development in the VMS role that you know, and you're talking to the physical hardware that you want. Likewise, for the network controller, you can have virtual NICs in the KVM-based machine that get you out to the systems that you need so you can bring stuff in, transfer it out, but you're actually developing the network driver. And then when you get the network driver, it's not starting. When you get the network driver to the point that you think it's good, my test would be to turn on the SCS protocol and see how well the driver actually passes real-time traffic. Which brings me to the point that I wanted to tell you about when, oh, there it is. Yes, okay. There's an RFID tag reader right here. A little red piece in the track right there. So when it hits this reader, there's another one over here. So when it hits that tag reader, we're going to see that the VMS program is tracking the position of the train as it goes around the layout. And if I scroll up a little bit, these are the actual connections that show the VMS data going in and out of RabbitMQ, which is on the Linux box for distribution. Now, there are two more videos I just haven't had a chance to edit. This is kind of a simple case, just following one set of cars around the layout. As you see that there's another one out there, if I start that guy, which I do in the other video, then the rule is you can't proceed from the block that you're in to the next block unless that block is empty. Since those engines actually do run at different speeds, the white circus train there will catch up to the orange train. And then what happens is VMS slows it down. And the system which is doing this is tucked right over here in this corner. Again, it's right at the edge of the model road. It actually built the list of the train cars that it's tracking based on the RFID reader. You go back to the beginning and look at this, the first time it picks up an RFID tag, it says it's a new set of trains that I haven't seen before. I'm going to start building it and keeping track of where it is. Certain cars, it uses a small in-memory database to do this. Certain cars have a property, like searchlight car, that says it's an end car. So when I read that, I say, okay, this group of cars is complete. If there's another one behind it, I'll find it or not. There is logic in there that says, okay, if the head car enters another block without an end car passing out of the other one, then I've got the case where I have a train made up of a number of cars, but the car at the end is not an end car. So then it says, okay, I'm going to end it for you, updates the track position. And you're actually seeing here, this is the control program updating what's going on and telling you the data values and stuff that it's reading. There is another RabbitMQ client, which may actually be tucked off over here that you can't see, that is camped onto the RabbitMQ message queue over here. And it looks like a little monitor display. It clears the screen, repaints it, waits for an update, paints it again. So what you'll actually see on the VT screen is you'll see this guy just progressing through the various points. And when it straddles them, it'll say both blocks are occupied, and this train is actually in both blocks. And then when it hits the end part, it'll move from here to here. The status will change to vacant. If there's somebody else behind it, then that block will be set to proceed. The nice thing about this is I've got a crack QA staff that can come along and test all of this. That was a picture I showed at the last boot camp. When my two grandkids come over, they run these things, and after they go, then I look at the log files and figure out where the program screwed up and then go and fix it. So they're my crack QA team. And don't ask me why, but when I saw the original VSI video, what hit me right away was computer controlled model.
Well, this falls back to the lab.
I remember that presentation where the professor had a grant to do a process control course, and what he did was the environment that he was controlling was a model railroad, and he presented that at a DCIS. I remember that presentation. What was also cool about it was he had other departments involved. He said the botany department came around and put foliage on the model railroad. The paleontology department came around. He had little dinosaurs on the layout. It was great. So it was really a multi-discipline course. I'm not sure if it was MIT. I thought that he was from Carnegie Mellon. But yes, I do remember. I still have his business card. But go take a look at the website. It's online. You think you might want to play with this stuff, let me know. The website has an email address, which actually goes to the same a2hosted.com address. What I discovered, unfortunately, even though it's configured to let me know that somebody sent an email there, it isn't doing it. So you've got my real email address there. You can send it to both places. I'll eventually get it. I'm going to go back up to the room and play with the DFI system. Oh yeah, how I got patches over there. How I got patches to the original UP2 professional system. This was before the drivers got checked in and built as part of field test. So on my integrity server, I've got the zip file downloaded that have the new drivers that I want to get over to x86. On the x86, I've got a system that can't talk to anything except the serial OPA0. Don't have anything like Kermit or anything. So I'm thinking, how do I get this zip file from here to there? The one thing that both the integrity system and the x86 system understood was the UEFI partition. Unfortunately, the UEFI partition on the x86 system is not big enough to hold anything else other than basically the boot manager and a couple of little EFI shell programs. It's a pain to expand that because it has to be contiguous. So I said, I wonder if. So using UEFI, using EFI-CP on the x86 system, I created sysdollar maintenance. I created the file sysmate sysdollar-maintenance.efi, the diagnostic partition, the one that the integrity VMS install procedure says I'm creating that when you initially do the installation. That is like a 60 megabyte partition. And EFI-CP on both x86 and integrity, well, they're behaving the same. So after I made sysdollar maintenance on the x86, I do set boot. And then using set boot -s, I look at the global partition block. And now instead of having FS0, which is the low part of VMS, FS1, which is the partition in the middle that understands, and you have FS2, which is the top part. If you look at it, it says lower EFI top. Now I have FS4. FS4 is the sysmain partition. So I take a USB stick, put it into the integrity using, don't remember if I did, using EFI-CP on the integrity. I moved the zip file from the integrity into the USB stick. Then I take the USB stick and I go over to the x86 system, and at the EFI, I use the shell commands to copy it from this partition on the USB stick into the sysmain partition on the VMS disk. Then I boot x86 up, use EFI-CP to mount sysmount.sys, and now I can use EFI-CP to copy the zip file onto integrity VMS, unzip it, and I've got my two driver images. I told that to Gary Newstead, who takes care of the boot manager, and he looks at me and he says, "We still do that?" That, I think, is a testament to OpenVMS's backwards compatibility. I said, "Yes, you still do that, and please don't take it out."
Interesting.
Yeah. I'm having a lot of fun with it. Next driver I'm going to work on is the I2C driver, so I can connect current and voltage monitors to it. I got some work to do in the GPIO driver, so it will automatically take care of resetting the GPIO pin level after a certain period of time. To actually do that right, it should be an asynchronous QIO request, and the IO doesn't complete until the pin gets reset. That means taking the driver and using the alternate entry point and having multiple IO requests outstanding on the same device at the same time. That's a little too much work. So I'm probably just going to have it complete, have an internal timer routine that goes back and just sets it off. If this ever comes to the point where other people want it, then I probably have to go back and fix it. And I really got to figure out a way to get to that hidden piece of data, that hidden PCI device that Intel is hiding, because that's how I'm going to be able to do GPIO input. I can do input now, but it's synchronous. That's how I'm going to be able to do input and interrupt when the signal changes state. I almost brought this stuff up again, but we didn't have time last weekend to set it up. The other problem I'm running into is I have an outside railroad that goes to the inside. So I've used up pretty much all of my long track. There are weatherproof RFID readers that will work on an RS-232 interface. So they're going to go outside. And if you want to see something that's interesting, do a Google search for G-scale in the snow. And you will see endless videos of people running G-scale modern railroad. G stands for garden.
Yeah.
Out in the snow.
Yeah.
They've got snow plows on the front of them. They've got snow blowers. It is really fun to watch. These guys do hold up to the weather very well. You just got to be careful of the ones that have electronics in the engines. The plan for next year is to actually build an engine house outside so I can pull them in when I'm done and not have to take them in overnight. I have to figure out how to get from the lower patio to the upper patio so we can have lower and upper loop. When I do that, I'm going to have two of these systems that are talking to each other so they can hand one train off from one section of track to the other. And ultimately, plan is to take the inside railroad. That's my family room right now. My wife is more than patient with letting me keep it there. Eventually, that's going to go into the basement, and there's a basement window that I don't use. The track is going to run outside, so the inside layout will be able to send train to the outside layout. And there'll be a group of these little boxes controlling the inside traffic, talking to the outside, saying, you've got something coming. Then at the end of the day, I can just say park, and it's going to figure out how to send everything back inside. But proof of concept, it works.
Same application you can use for controlling greenhouse.
Yep.
Just change, same thing, same thing.
Commercial building control. The stuff that Johan's brother does.